Welcome back to another HVAC Engineering-Techie channel training video. Remember that these training videos are educational in nature, intended to help you in your career. Remember that this channel talks all things HVAC, from engineering design, construction, equipment, systems, tab, controls, efficiency, and performance, and are intended to be information that all technicians need. Doesn't matter whether you're an installing technician, a service technician, a test and balance technician, a designer. All those things that we talk about are important to those people. So today's lesson is about HVAC commercial package systems. So in the last couple of videos we talked about residential, now we're talking about commercial. So these will be a little bit bigger units we're going to talk about. Before we start, please become a subscribing member if you haven't already. Remember, this costs you nothing. No one will ever bug you about it. It's free. Just hit the button down below that says the black button that says subscribe, and give me a thumbs up if you like the videos. These are important to me because Google uses those to evaluate the channel, which keeps me on the air. I really appreciate it. So let's get started talking about commercial package units. Thanks. So now we're going to talk about commercial package units. And if you've already taken the residential one, these will be similar except have a lot different features. Now, the one thing about package units, whether they be residential or whether they be commercial, buying a package unit is like buying a car. You buy the car, it has all the necessary components, but it may have some options. Well, package units are basically the same. They have the standard package units that they make all the components, but they do allow some options in and out. But it's not like an air handling unit. An air handling unit is basically a customized built unit every time, whereas a package unit, it's not. More like buying a car. So here's a standard commercial package unit. It has a blower unit to produce the air. Normally they're a draw-through arrangement, not always, but can be. And they go down to the space, up from the space to the return plume through the filters. This one has an electric heater and through the evaporator coil. It has a condenser section, which has, this particular one has two compressors in it. It'll have condenser coils for those. It has receivers for the refrigerant. It has condenser fans, and it has an electric heater in it, and it has an evaporator coil. So these are just like those residential units we talked about that have a terminal board inside the unit here. And remember, the unit has its own internal controls that runs everything within the unit. It has all the refrigerant safeties, has compressor control, it has a condenser fan control, and it has any control of solenoid valves or anything in the refrigerant circuit. It has controls, its own control system for that. But it also has these lugs, and these lugs basically are for a thermostat to be able to run this unit, or a DDC controller we can put on that. And this is very similar to a residential one that has a power wire. That's the power coming up from the unit. And this unit goes, 24 volts goes over to the unit thermostat, and the thermostat has different controls in it. It has here in this terminal board has a green. The power ones are for red, and this green is for fan. So if you have fan control, the power goes over to the thermostat. The sub base switches it. If it's on, switches it on. Then it puts power to this green terminal, which then powers the fan. For cooling, this has two Y1 and Y2, and it has W1 and W2. So Y is cooling for yellow wires, and W is for white for heating. So this has two stages of cooling and two stages of heating, and it has a common wire. Again, the common wire is used if the thermostat has anything in it that needs power, like a computer, or has a display or some things like that it needs a return for the common. The reason a regular thermostat, for a thermostat that has either bimetal unit in it or it has a mercury bulb in it, they don't need a common, because all these are commons. It just makes the circuit back. But if you need to use power here, like for a display, or if it has a thermistor that has a computer component in it, then it'll need a common to run that thermostat, but not to run the unit. So this is a normal temperature control. Now the refrigerant circuit on this has two circuits. So what happens here is that we have two compressors. So one stage, we go ahead and start a compressor. It takes the gas from the suction gas from the coil, and it has two coils, so it's got supply piping and return piping, and so the return piping, the suction for that coil comes back to its compressor. Its compressor pumps that suction gas into hot gas. Hot gas goes to the condenser coil, goes into the receiver, out of the receiver, and through the solenoid valve to its expansion valve. And then it cools this coil, and then it goes back. If you need a second stage, then it brings on the second coil and does the same. Now, if you've taken S1, the standard package unit basics, it'll explain all these coil arrangements and all that to you in very detail. But most of the time what happens here is they have a solenoid valve. And the reason they do that is that they have these compressors controlled off of discharge pressure. So when they want to stop this coil, they close the solenoid valve, but the compressor keeps going, and it keeps pressurizing the gas, and what it does, it fills up this receiver until it gets above a certain pressure, and it turns the compressor off. And they have check valves here, so what happens is now we have gas pressure on the backside of the solenoid valve. So when the system says I need cooling, it opens that solenoid valve, and we immediately have gas of a liquid refrigerant to the expansion device to be able to start the cooling immediately. If we didn't do that, then what we do is we have to wait for the compressor to pump up get this vapor, pump it up to hot gas, get the hot gas to the condenser coil and to the coil. So there's a lag, but with these solenoid valves, we don't have a lag. It's immediate. And these are the refrigerant circuits. Again, remember that I've shown the refrigerant section over here, but they can be anywhere. They can be beside the unit, they can be on top of the unit, they can be around the unit, you never know. So anyway, I've shown it just this way for clarity. Remember that the thermostat has a sub-base. The sub-base has at least two switches. It may have more. But one switch is normally unit on and off or auto, so the unit can come on and off. And they also may have a fan switch. It says exactly the same thing, on, off, auto. And we may have a system switch over here that says heat, cool, or auto. So you can put it in heating only, but in cooling only, you can put it in auto. And these sub-bases allow the user in the space to be able to turn this unit on and off. However, these older type thermostats are not the preferred, because when you switch the unit on and switch it to cooling, it's in cooling and it's on. It's on. The compressor will cycle on and off to maintain temperature, the set point of the temperature, but the unit's on, so it doesn't go off at night. It runs all night long. And this is very, very energy inefficient. So basically, we always want these to be programmable thermostats, so we can say, we want it to start at 6 a.m. in the morning, we want it off at 5 o'clock at night or 6 o'clock at night. And we can do that with a programmable thermostat. We can also do a setback temperature, say during unoccupied hours, we wanted it at 80 degrees in the space or 65 degrees in the space. And so we can do some energy management with a programmable thermostat. Or we can override the system with a DDC control system. So now we put relays out to all these points, so we can now run all these points. We also put a room sensor on it, and we can also put a discharge air sensor as a status point. Discharge air temperature is the best, cheapest unit status point we can get. It doesn't tell us what's wrong with the unit, but it tells us if it's working or not working. If it's supposed to be cooling, it'll tell you if there's cold air or not. If it's supposed to be heating, it'll tell you if there's warm air or not. Now, what's upstream wrong with it, we don't know. I mean, it could be, in cooling mode, it could be the fan belt is broken, the fan's not working. It could be that compressor's broken, not working. It could be there's a leak and no refrigerant in the system. It could be the filters are totally plugged, there's no air coming down the system. It could be a lot of different things. But at least you know it's not working, and then you can send a technician up to figure it out. That's why we use those status points. Also, you can use a network connection if the unit's set up for it. Some units have internal control. All of them have internal controls, but some have internal controls that have network capability. So you can hook a network into it, and now you can see everything that's going on here. Now, you may not be able to control the refrigerant side of it, which is good, but you'll be able to see what compressor's on, what's not on. You'll be able to see what condenser fan's on, what's not on. There's a whole bunch of points in here you can see. I don't know why you want that data, but you can see it. And so that takes a network controller that's able to communicate and put it on your network so you can see it. And to do this, now we have some extra points, so we need a controller out here also. Some network controllers have points on them, some do not. If you don't, you add another controller here. You can take a room sensor, you can take the supply air temperature sensor, you can run this outside air damper to be able to give ventilation air. And so those are the three choices you have in controls. You have a thermostat, you can have DDC, or you can have network control direct. A typical control sequence, and again, remember these sequences are high-level sequences intended to tell you how it works, not an actual sequence for a programmer, because they don't have exit points, they don't have some delay timers that might need to be in here, and there's some other things it doesn't have. So they're just to see how it works. High-level sequences. These are similar to what the engineer would have on his drawing. So the supply fan the outside air damper shall be open anytime the system is in the occupied mode. Stage the compressor to maintain the room temperature cooling set point. Stage the electric heater to maintain the room temperature heating set point. Maintain room temperature and supply air temperature. Now, another thing to notice here on package units, they're all constant volume units. There is a VAV unit, we'll talk about that, but all standard units are constant volume, meaning this fan is not a variable speed fan, it's a constant volume fan. And the reason for that is compressors don't like variable flow air over their evaporator coil. The reason is because this gas coming back needs to be vapor. It can't have any liquid in it. It can have, it has lots of thousand little droplets of refrigerant that have heat in them, but they're not coalesced together to actually provide a liquid. If you bring liquid back to a compressor, you can damage the valves in the compressor, or if it's a scroll, you can actually damage the scroll plate. So basically, we don't want liquid back to the compressors, and so that's why they're all constant volume. So then you monitor the room temperature and supply air temperature because we have those monitoring points. Now let's look at a package heat pump. A package heat pump's the same. It has the fan, the coil, but it has another device in here. It has a reversing valve on each circuit. And the reversing valve basically makes the condensing coil the evaporator coil and makes the evaporator coil the condenser coil. Now, if you take S1, it'll explain all the refrigerant of a heat pump circuit and what's in it, what's not, and how it exactly works. Is it over there in S1 to do that? So this has, of course, the air comes from the supply fan down the space, comes back in, goes through the filters, goes through the evaporator coils and back, and that's the air circuit. Refrigerant circuit again takes the suction vapor and puts it in the compressor, pumps it up, makes hot gas. The hot gas goes to the condenser, through the receiver, and to the expansion device, cools in the evaporator coil and back. If it's in the heating mode, in the heat pump mode, the compressor takes the suction vapor. It actually takes instead of it, the four-way valve makes the suction coming from the coil, the condenser coil, and it takes it and pumps it up and pumps it up to the evaporator coil, which is now a condensing coil, and it basically is hot gas. So it's hot. It's not going through the evaporator. It's not going through the expansion valve. It goes around the expansion valve, as you'll learn in S1, and then it provides heating, and then the suction, which now is cold. It was hot, but now that it's down, and so it's a vapor, it's a saturated vapor, goes back to the compressor, and that whole thing starts over again. And then, of course, when it pumps it up, it goes here, and it expands here to cool this, and it sucks heat out of the outside air, no matter how cold it is. There's some, this could be really, really cold, so it sucks it out of it. And S1, again, I'll explain all that refrigerant circuit stuff to you. Again, the control is by thermostat. It has the points. This one, again, is two-stage. This one it has heating two-stage because we use the compressor to heat. So again, it has a thermostat. Now this thermostat must be a special thermostat because it has to know that this is a heat pump which has a reversing valve. So unlike an electric heater, which you just need 1 point to turn it off the heater, this needs 2 points. We have to turn on the compressor and we have to turn on its associated reversing valve. Now there's another problem here in that the manufacturer can either make the reversing valve power to heat or power to cool. So it depends on whether it's normally open, normally closed valve or not. And unfortunately, this is not standard. I want it to be on when I put power on it. When I put power on the reversing valve, I want it to go to heat. And when it's off, I want it to go to cooling. So I want to fail in the cooling mode. Many don't. Many fail the heating mode. So you got to know what it is. And these sub-bases, the thermostat has to know which is which also. Does it put power to it for heat, or does it put power to it for cooling? Because I can't tell you, because every manufacturer might be different. I wish that wasn't so. You can overlay it with a DDC system by wiring the relay outputs to these different points. And remember, this has a green for the fan. It has 2 Y's for the cooling. It has 2 W's for heating. And so that normal mode, just like the rest. Again, you can have network control. We have in the unit has a control panel that's capable of network communication. Not all of them are. So some of them are, some of them aren't. You can put a network control down to it, and now you can see what's going on with the machine. Now you can also, through this network controller, can program start-stop points and things like that within the unit when you want it occupied, non-occupied. However, I like the network controls, no problem, but I always prefer start-stop of the unit to not be network. And I want it on a hardwired, dedicated hardware. The reason is if there's any blip in your network, if for any reason, whatever it happens to be, then you lose total control of the unit. You can't turn it off, which I think is not good. I know in the commercial, in the industrial world, we never allow network controlling to do key on-off because of safety. So anyway, I like to have at least one controller with a start-stop. If nothing else, I want that start-stop. And then, of course, the controller will run the outside air damper, will run the room sensor, and the supply air duct sensor. So we will do those points on this unit. So there's 3 different types of controls, just like all the rest. The sequence would be the supply fan, and she'll run, and the outside air damper should be open to the minimum position anytime the system is in the occupied mode. Stage the compressor to maintain the room temperature. Switch the reversing valve to indicate heat mode to maintain room temperature during heating. Monitor room temp and supply air temp. So it's a regular heat pump. Okay, now we can have a package unit with some of the options. Now, commercial, a lot more options than residential. Residential, if you want an economizer on it, you have to normally buy a third-party component bolted to it, or else the manufacturer will sell you a third-party component bolted to it. And all that means is it's not basically controlled by the unit, it's only controlled by outside control. So what happens here, this happens to be a heat pump with an economizer. So what the economizer section is it has dampers in it to allow induction of 100% outside air, goes to the unit, goes to the space, and comes back and exits this relief damper when it's in economizer mode. So now we're using the outside air to do the air conditioning effect of the space. We're not running the compressor. Now this one shows an exhaust fan on this relief. And the reason is when we're in regular mode without any of this on, the air goes out, comes up, and goes through this return air damper back to the unit. So this supply fan is running all the pressure to be able to circulate the air in the space. When we go to economizer, this damper closes. The air comes in here, goes through here, and comes back. Well, if we didn't have this fan here, then this fan has to pressurize the space enough to push the air out this damper. Now, when we're in regular mode, this fan suction, this return was under negative pressure. It's seen the suction of this fan. But the minute we close this damper to an economizer, this suction pressure is all used to draw this air in. So there's none here. So you'd have to pressurize the space enough to push it out of this relief damper, which normally blows the doors open. I mean, it doesn't blow them all the way open, but it blows them open an inch or two, and we start discharging air outside, and you see it all the time when you go in a store. I always check, having been a balance guy, I always check when I open the door, when this building's under positive and negative pressure, does the air, when I'm coming in the building, does the air hit me in the face, or does it hit me in the back of the head? And if it's in the back of the head, it's a negative building. If it hits me in the face, it's a positive building. And so that's why, especially during economizer, this is supposed to operate to maintain the same pressure. Now, we can do that even without fancy controls, because we can, since this is only 2 conditions, one is in regular mode or one is in economizer mode, I can, and this is not VAV, it's constant volume, we can balance the system so that with this fan on and this damper open, we can balance the linkage damper down, that we can always guarantee the same pressure here as we would in normal operation. So it's a balance condition that we could do that. This again has thermostat or DDC control. This would not have thermostat control for this because the economizer is too complex for a thermostat. So we'd put DDC on it, we'd have outputs here, and then we'd be running these dampers right from the controller. We'd have a room sensor. This particular one, I put a room pressure sensor here, but you wouldn't really need it because it's constant volume. One of the problems I've had before on these units, but that would be on a VAV, if it's a constant volume, you should not have any problem if we balanced it properly. We wouldn't have a problem. This one actually has a room pressure sensor, so it could actually modulate this fan speed if it had a VFD to be able to speed up or slow down to make that pressure always right on the money. So you could do it either way. Again, we have a room sensor, we have a supply air duct sensor, and on this one we have a return air sensor and an outside air sensor. That's to run this economizer. Now this is a dry bulb economizer. Dry bulb uses the temperature difference between the outside air and the return air to decide when to go in and go out of economizer. There is another kind, which we'll show on a unit in a little bit, which is an enthalpy economizer, which is using the total heat of the air and the total heat of the moisture in the air, which is a little more accurate, but has another issue, and we'll talk about that when we get there. Okay, so here's a sequence for heat pump mode. Again, you can use a network just like you could a DDC either way. The supply fan shall run and the outside air damper should be open to minimum position anytime the system is in the occupied mode. Stage the compressor to maintain the room temperature. Switch the reversing valve to initiate heating mode and stage compressors to maintain room temperature during heating mode. Modulate the outside air dampers, start the exhaust fan, and modulate the relief and return air dampers to maintain building pressure set point and ventilation air difference between relief and outside air shall be equal to minimum ventilation air. Okay, so that's when we're going to start into. So if you had if you had this economizer and you started up in normal air conditioning mode and your pressure wasn't correct, this would change the openings on these dampers to maintain that pressure. You could do that, but it's really intended for this. If the outside air temperature is 5 degrees less than return air temperature, enable the economizer mode. Modulate the outside air return and air relief dampers to maintain the room temperature set point. While in economizer mode, start the exhaust fan if the building pressure raises to 0.02 inches above set point. Turn the exhaust fan off if the pressure drops to 0. If the outside air temperature drops below 40 degrees or the outside air temperature increases to 2 degrees less than return air temperature, disable the economizer mode. So what we're doing, if it gets cold enough outside, we switch the economizer. When it gets to the point we can't get our energy out of the outside air we want, we go back to regular air conditioning mode. Monitor the room temperature, supply, return air, and outside air temp. So this is a fairly event. Now, another reason we don't want economizers running on unit controls, I mean, there are some units that will sell you a unit that's totally off there. They put enough fancy controls in here to run an economizer. Well, the reason we don't like those is if you have 10 units on a roof serving in an office area that has big areas, and each unit is running its own deal without a network. So one might be an economizer or one may not be an economizer. And if the set points are slightly different or if the calibration of the sensor is slightly different, you could have them fighting each other. And we don't want that. So with a third party, or doesn't have to be third party, but a DDC controlled network running them, we can make sure that that doesn't ever happen. But you can't do it if you have separate controls in each one of them and they're not talking to each other. So we prefer an outside control to be running this system. Okay, so now we have computer room air conditioning, which is computer room air conditioning CRAC units. And a CRAC unit is a self-contained unit. It has a compressor. It has everything in it it needs to run except for a condenser. And outside we have a condenser coil. Now the condensing unit for these, the compressor's inside. So we run the hot gas and the liquid out to this coil, which has an air fan on it. So as we take the suction gas, run it to the compressor pressurizes it, heats it up, makes it a hot gas. It goes to the condenser coil, turns it into liquid, brings the liquid back to go to the cooling coil. Now these are computer room units, so we've got a whole bunch of heat in the space. We never need heating. We only need cooling, and we don't need dehumidification. There should be no reason we'd ever need dehumidification. There's nothing in there that's going to make humidity. Now, if the outside air is so high that you have to have it lower than in here, then you'd have to put a dehumidification system on the outside air, make up air to the space, and dry the system that way. But normally they don't ever need they need humidification, because we want to see 30-35% humidity in the space to prevent static electricity from sparking. If you have media, magnetic media, and you spark it with your finger, you can destroy the data that's on the media. So it's really important. They keep the humidity level slightly higher in these spaces. The way these work, this is a self-contained unit. It has a supply fan. The supply fan draws the air down from the space through the cooling coil, through a chamber, to humidity chamber, and out, and blows it underneath the floor. Now, we have raised floors in these computer areas to be able to run a lot of cable or fiber optics down here below them. And we use that space to deliver this air. And we deliver this air into spaces. Now, we don't control these systems with outside controls. They have their own control system, and they run run temperature and humidity in the space very effectively. They don't need any outside controls, but we do sometimes monitor them with a network integration. So that's available to just network them and bring them together. So this computer basically cools the racks, underfloor supply air fin. Racks have hot and cold dials, and I'll explain that in a second. Return air can be from the ceiling return air plenum. They come in 5 to 25 ton capacity. There are small ones. These are called mini-mates. They go above the ceiling and basically blow the condenser air into your space, which we don't use those unless you really have just some little spot you have to do. But what we do is we do a whole bunch of these. So like if you have, 100 racks inside your computer room full of servers, we will put probably 30 or 40 of these around the space in line with those racks to be able to provide cooling under the floor for these spaces, for these racks. I already talked about that. These always run 24/7, so there's no schedule involved. You can integrate the building controls. They're available with chill water and DX. Normally DX is the preferred version, and that's because chill water might be economized in the wintertime to make it a little warmer. Well, this ain't going to work for this. These are 24/7 for total heat load that never changes. So that's why we normally have DX. You can run chill water and DX, so one is standby the other, but normally the DX is the preferred method. Now here's how they work. So here's your raised floor system. Here are the computer racks, and then these have a whole bunch of servers. And every one of these little computers has a little muffin fan on it that sucks air in from one aisle and blows it out the other aisle. That's on purpose. So what happens is this cold air from the computer room unit is underneath the floor, and we'll put perf tiles right here between these two racks, making this a cold aisle. And I mean, it can be cold. It can be 68, 65 degrees. You can feel it when you're here. And then it comes out a hot aisle, and over here it may be 80 degrees. Much more comfy. But remember, we're not cooling for people, we're cooling for the machines. And this rises. On most normal rooms, in the past, we've just let this air drift over to come be sucked out of the room from this return. These units are normally about 6 foot tall. Could be 5 or 6 foot tall, so not terribly tall, and you got space up here. But the way I prefer to do it is if we've got a return air plenum above the space, I like to put a perf grill right here and let this hot air drift up, which it naturally does because heat rises, up to this grill, and it runs to this. And then I take a duct from this up to the ceiling, and I put this under negative pressure. So all of these units are sucking air out of this plenum area, and it's sucking it out of the hot aisle. So we don't allow the hot and cold air to mix, because there'll be a cold aisle over here and a cold aisle over here, then a hot aisle. So this segregates the air very well. It works really good. And so you can actually put that in the space. So, I mean, sometimes people I've seen where they've ducted this up to the ceiling, and all these fans blow up instead of out of a side. And then the cooling is down below, so the cold air comes through and goes out that way. That's possible. But this is, I like this better because there's more air capacity available. The size of the floor, the depth of the floor, is actually dictated by its tier level, what tier this data center is. But basically, these are normally 24 to 48 inches. And why the height is because it depends on how many cables you're going to have under here and how much air we need to push up here. So it depends on how many of these are. Now the trend has always been that the computers get smaller and smaller, more dense and dense and dense. So we get a lot of servers, but unfortunately the heat inside the server rises. Now what's happened over the last 3 or 4 years, which has been good, we used to say that the computer people said we wanted 72 degree air minimum to be into this unit. Colder is better, but not hotter. Well, nowadays they've realized that they can live with up to 90 or 95 degrees at the server itself. So they've allowed us to raise these temperatures, thus saving energy. So this may get now to be 85, 89 degrees over this side, and this may be 72, 74, 75 degrees. A little more reasonable in the temperature range. There's one other control component that's installed here, and normally we have a water detector, which is a cable that you surround your unit with down here, and it detects if there's any water in this unit. There should not be any water coming down here unless there's a problem. So we detect that water. And we use those mainly on chill water units, but they can also be used on this because we don't want water down here. This is not a good idea to mix all this cabling down here with water. Typical sequence is pretty simple. Supply fan shall run anytime the system is enabled. The internal unit control panel shall stage the compressor and humidifier to maintain room temperature and humidity set points. Unit shall be integrated into the monitoring system through a network integration. Upon receipt of a unit alarm, the unit shall shut down and alarm shall be sent to the operating staff. Monitor the room temp, humidity, and run hours. So we don't actually do much with this. The one thing we use this network integration for is to set points as humidity set points all exactly the same. It's really an irritating problem if one of these is set different than the other, then they're fighting each other. And when you have 20, 30 of them in the same room, it's really difficult to do it manually. So these integrations work really well. And the other thing we use it for is status of the units, what's going on in the unit. The units are really good, really dependable, and really accurate on temperature and humidity. They're very good units, but the only problem area is the humidifier. Because the humidifier uses water. It's not the humidifier's fault, but water's corrosive, water's dirty, water has lots of components in it, and so they're a maintenance issue, the humidifier, and so we have to keep an eye on those. So now we're going to talk about a package VAV unit, a package unit that's designed to be variable flow. So this is a special beast. For an air handler on chill water, VAV's piece of cake. It's no big deal. Just strap a VFD on the supply fan and you got a variable speed unit. On a package unit, that's not the case. I think I mentioned this earlier, or maybe I didn't, but it's always assumed with air conditioning guys like me, technicians, is that chill water and hot water is complex. It's hard. And package units, they're designed to work for the factory. They're simple. Well, it turns out it's exactly the opposite. The package unit is much more complex, much more difficult to maintain and keep working correctly than a chill water and a hot water air handling unit, which is plain simple. So these, we'll go through the complexity of what's going on here. So basically we have a supply fan system, we have a return fan system. So the air from the space is induced by the return fans, comes through here, goes into this chamber, and if we're in normal mode, it goes through the return air damper, through the filters, through the cooling coils, through the electric heater coils if it's got any, through the supply fans and back to the space, and this is the circle. We've got a full economizer here. Now these are variable speed, so we've got we have a supply duct out here that has VAV boxes in every space. So as these start to close, we have a pressure sensor on the supply duct, and it starts to slow down these supply fans because they don't need as much air, and thus they economize. That's why these are more efficient. Well, the way this is balanced, so you'll know, when we balance this, the balance contractor balanced these valves with them all at design flow, full flow. There's complexities here I won't go over, but anyway, it's here. And then we have a differential pressure sensor here, and it's going to speed this fan up or slow it down to always maintain that pressure set point. This pressure set point is established by the balance contractor to get enough air out of all these VV boxes at the same time. Now there's such a thing as diversity, which I won't go through, which is in the tab courses. If you look at the one that's balancing a variable volume system, it explains how these are all set up. We don't, for this course, we don't need to know that. So basically these are balanced so that these will always work even if it's a full flow. This is the pressure. So if we keep that pressure, we know this will always work. And as these start to close, this pressure wants to climb, but this sensor says, nope, slow it down. We don't need any more pressure. So it'll start slowing these fans down to maintain that pressure. Now, when we start slowing down the supply, we got to slow down the return because it's, this is volumetric. This is looking for a certain volume, and now all of a sudden, if this is set at full speed and this is at half speed, we got a problem. So what happens is these fans are actually scheduled, and they'll go over the sequence in a minute, but it actually follows these supply fans with an offset. So in other words, the offset is how much fresh air we want. So if we need 10,000 CFM supply air and we need 2,000 CFM of fresh air, then our return fan should be at 8,000. So 10,000, 8,000, 2,000, this makes up 10,000 because we have to induce this outside air into the space. So that's the way we control these return air of fans. Now these are shown as fan arrays. So basically now we're talking about this is a package unit. So now we've got cooling coils, evaporator coils, we've got condenser coils, condenser fans, and compressors. And of course we've got an internal control system that runs this whole thing. So on these here, they don't have thermostat lugs because this is way too complicated. A thermostat cannot run the system. It must have a DDC control system to run it, and it might be internal like this one. A train will do an internal one, but maybe not. Maybe you just need to have an outside one. But most of these will all take a network control inlet. So basically we got compressors, so we take suction gas from the cooling coil, we pump it up, make it hot gas turns into liquid, the condenser coil goes to the stages where it provides liquid refrigerant to the expansion valve, which expands it, making it very cold, and it absorbs heat out of the air, making air conditioning, making it cooling. So that's a standard system we have here. These could be quite large, so they might have 4 or 5 stages, or it might have a modulating compressor in here instead of this. So a typical sequence for this system would be the supply and return fan shall run any time the system is in the occupied mode. Modulate the supply fan speed to maintain the supply air duct pressure set point. Modulate the return fan speed to track the speed of the supply fan offset by an amount equal to the minimum outside airflow. Modulate the minimum outside air damper to flow set point of outside air flow meter. Modulate the outside air relief and return dampers to maintain building pressure and ventilation air. All right, so here's the deal. So this could be a 20 or 30 ton unit. So it could have a lot of air moving through it. And these dampers, these economy dampers, are capable of taking the total flow of the unit. So it's total flow in and total flow out. So they're quite large. Well, the problem is dampers tend to leak. I mean, they're low leak dampers, but that doesn't mean no leak. This means very low leak. So what we normally do on a package unit that's VAV, and even an air handler's VAV, is we put a small ventilation air only damper. So it's designed at full flow to be the design flow for the outside air. Because what happens, this is VAV, as this fan slow down, the outside airflow slows down because it's being induced by the pressure in this plenum. So basically it will never get exactly what ventilation we really need. So we put a separate damper there with a piece of duct, small piece of duct with a flow meter in it. And we run this damper off that flow meter, which set point happens to be minimum ventilation air. So we know we can't open it any further, so we design it such that at minimum flow, with this damper open and this fan at minimum flow, we always get the ventilation air we need. Now as this speeds up, it'll start closing the damper so we don't get too much ventilation air. And that's what this sequence is about, is getting ventilation air in a VAV that actually works. If you don't have this minimum damper, it gets complicated. And the tab guys have a terrific time with it. You have to set this damper up with stops. Now you can't physically stop it, but you say, okay, now when the unit's off, this is 100% closed. When the unit's on, at this speed, we want it to open this percentage. When the fan speeds up, we want this percentage. And we try to guess what that is. We never get it quite right. It's impossible to get perfect. But on this situation now, these are controlled totally separately, and we can't do those. Now, I would mention to you that this also has a room pressure set point. Pressure sensor, which allows us to actually manipulate this to maintain building pressure. Here's the rest. Stage the compressor and modulate the compressor speed to maintain the supply air duct temperature set point. If the supply temperature drops more than 2 degrees below set point, stage the strip heater to maintain supply air duct temperature set point. So what's happening here, we not only have variable speed, we have variable speed compressors, which is making it a better unit. So we can actually slow these compressors down, so again, probably not freeze up a coil. Not slug a compressor because we got too much refrigerant in the circuit. We can slow that down. This one also has a hot gas bypass, which means simply if this gets too cold and we start trying to freeze up a coil, it will take this hot gas and inject it right downstream of the expansion valve, heating it up to keep it from icing. So that means that we can run this in really cold temperature. We can air condition in cold temperature. So insert the supply air temperature set point based upon reset the supply air temperature set point based upon the connected load. Every 5 minutes, if any box damper is greater than 95% open and no box is less than the minimum position, then lower the set point 1 degree. So as long as we have boxes above 95% and we don't have any down at minimum, everybody's need cooling, then we will lower the supply duct temperature 1 degree to get a little more cooling down to the space. If no damper is greater than 90% and one or more dampers is at minimum position, then we'll do the opposite. We'll raise the air. If it gets too cold in space, we'll raise it 1 degree. And the reset will be 55 to 70 degrees. And that works really well. Now, this sequence is actually a lot more complicated than this. And we can have it go down faster, up slower. There's a lot of things to consider here. We can actually have some of the sensors vote. If this was 2 degrees out of temperature and these are half degrees out of temperature, this one gets more votes. I'm not going to go into that complexity, but it is in there. Now here, this system also has a dehumidification mode. If the room humidity rises above 60%, enter the dehumidification mode. Modulate the compressor speed to maintain room humidity set point of 55% and stage the electric heater to maintain supply air temperature set point. If the room humidity drops below 50%, then return to normal room temperature mode. Modulate the outside damper to maintain the flow meter set point, which I already talked about up here. So what's happening here in dehumidification mode, these sensors on these boxes are both temperature and humidity. So if they start sensing humidity above 60%, then it will turn the compressor on and drop this coil to really cold temperature. And it will drop it probably down to 48 degrees, whatever the maximum coldest temperature you can get with gas. It might be 48, might even be a little colder. And it will start wringing a lot of water out. And as the humidity in the room starts to lower, and it gets down to 55% from 60%, we'll start modulating this to maintain that humidity in the space of 55%. When the humidity lowers to 50%, we're going to stop it and go back to normal air conditioning mode. To make this work, we have to have reheat somewhere in the system. Now, we may have strip heaters down here at these boxes to provide reheat down at this level, but these are not normally large enough to do major dehumidification. These will reheat a space for comfort, but they aren't enough to really do the unit. So we have to have heating in the unit. This could either be electric heater on an SCR, or it could be a hot water coil from a hot water system. Either way. And what we're going to do is we cool this air down, drop the humidity out, and then we take the temperature and rise it up here so we don't freeze the people down here. We get now the temperature we need to supply to. Remember, this is a VAV system, so it's constant temperature, variable volume. So you can, if you get real cold temperature supply duct, you can freeze somebody out because this damper position has a minimum. The rest, so the ventilation air can come in here, can actually get way too cold. So we have a reheat in here to do that while we're in dehumidification mode. If the outside, now here's the economizer, and this happens to be an enthalpy economizer. And you'll notice it has humidity sensors and temperature sensors in the return air. It has temperature and humidity in the outside air, which is normally coming in from a global point. And it watches that for the economizer. So here's the, if the outside air enthalpy is 4 B2 per pound less than the return air enthalpy, modulate the outside air relief and return air dampers to maintain the supply air temperature set point of the mixed air sensor. If the differential enthalpy drops to 2 BTU per pound or less, or the outside air is below 40 degrees, return to normal cooling and heating mode. So this is running the economizer. Now, remember that with a humidity sensor and a temperature sensor, we can calculate the enthalpy. And what we're trying to do is we're making sure that the enthalpy of the outside air has enough space where we can actually use that to cool the building, enough energy so we can cool the building with that. And that works really well to do that. The only problem we've ever had with these is that humidity sensors get out of calibration much, much quicker than a temperature sensor. And the problem is commercial building owners do not calibrate their sensors. You know, in an industrial project where we have a process, we may calibrate the sensors every quarter. And so basically they're watching those a lot. Of course, they're much more delicate sensors and much more expensive sensors and much more accurate. But we're keeping them well calibrated. But in these commercial buildings, no one goes up to calibrate their sensors, which they should, but they don't. I mean, at minimum, they should calibrate them every single year. In some cases, maybe 6 months. So what happens if these get out of calibration different than the outside air calibration, now you can get the economizer working when it should not be or not working when it should be, thus not saving the energy it's supposed to. So enthalpy are much more problematic in keeping operation than a simple dry bulb economizer. Now, to be quite frank with you, I've done a lot of retro-commissioning in existing buildings, and the normal situation is to find economizers turned off. Most existing buildings, economizers are not functional. And the reason is something goes wrong, it's not working. The easy thing for an operator to do is turn it off, because they got to do something right now. You know, this thing is wasting energy, it's just blowing cold air out the economizer or vice versa, warm air out the economizer, and they just shut it down because it's too complicated to figure out right now. I gotta get on with it. I gotta stop this building from bleeding energy, and they will lock them off. And so when you get there, you'll see they're not working. Then you got to go figure out what's wrong with them. But economizers are problematic to keep working, and to do that, you need to keep the sensors calibrated. And that's pretty much it for a VAV unit. Now we need to go look at what happens in the room. So there's VAV boxes, and the VAV boxes used on a package system are exactly the same as the boxes used on a chill water and hot water system. The VAV part of it is not any different. So these VAV boxes basically take the air from the system, which, remember I told you is constant temperature, variable volume. So this constant temperature air enters the box, goes to the room. The room temperature sensor is connected to this controller, and it tells this damper where it needs to be able to cool or heat the room. Well, what happens, the tab guy has calibrated these sensors. This is a velocity sensor in here in the inlet cone of this box, and he's calibrated it to say the maximum flow of this box, this set point, this velocity pressure is this. And so this has been calibrated. So what happens if the pressure changes upstream, this damper will modulate slightly to make up for that pressure, but it will always maintain the CFM the room sensor wants to cool it. So it knows how to do that. And that's called, these are basically designed, a velocitrol produces pressure independent operation. So if the pressure goes up and down, the flow in the room doesn't go up and down. It only adjusts when the room sensor says I need more or less air. Supply air is variable volume, constant temperature. Hot water electric reheat, the coil heating is desired. So this I'm showing a strip heater. Now all boxes don't have them. Some boxes are cooling only, but at least all the perimeter ones should have a heater of some kind on it. And they actually make the, in cooling mode is variable volume, constant temperature. In heating mode is variable volume, variable temperature, because the heater can bring it up. So it's a little bit different. Sound attenuator, if you want it, you can do that. The sequencers are simple. Room temperature sensor modulates the VAV damper, and hot water coil and heat strip to maintain room temperature. Supply inlet velocity sensor maintains constant flow during inlet pressure changes, making the terminal unit pressure independent. Now there's more than one kind of box. This is called a series box, series fan box, and it has a supply fan in it that's constant volume. And it runs all the time. It's series, it's in series. Here's the cooling valve, and the cooling valve comes in and changes the air volume, and that volume goes to this fan, but this fan has constant volume. So the difference between these two, it draws in from the plenum. So the air to the space goes in this kind of circle. This fan is on anytime the unit's in occupied mode, so it goes this way. When we're in a cooling mode, this speeds up, so this air becomes less and less and less. This becomes more and more and more, but this air is always constant. And that's called a series fan box. Now, why do we use a series fan box? We use a series fan box for anything in a variable volume space that we need to be constant volume because of a certain specified air exchange rate or a building pressure rate. So if you have a room, like if it's a hospital bedroom that's isolation, it has to always have a constant pressure in the room, then you would need to use a series box. If it's on a VAV area, it has to be a series box. Or if you have a restroom, which requires so many air changes, then it will need to be a series box. You could also do it to have variable exhaust and variable inlet, but that's way too complicated. This is much easier to do. The velocitrol again provides pressure independent operation, uses interior heat, so whenever this fan is running, and this is down at minimum like in wintertime, then we're going to be able to use the heat of the plenum, and that's the heat of the lights, heat of the plug load, and heat of the people. Whatever's in that plenum, it gets to use that heat and recirculates it, but that's an energy efficient operation. Fan induces plenum return air when the fan is greater than the cooling CFM. Supply air is constant volume, variable temperature. Well, that's exactly opposite of what the VAV is, right? Remember, VAV is constant temperature, variable flow. Well, this box turns that into supply air is constant volume, variable temperature. Hot water electric reheat if you need it. Sound attenuator if desired. The sequence is the same. Room temperature sensor modulates the VAV damper and the heat strip or hot water coil valve to maintain room temperature. Supply inlet velocity sensor maintains constant flow of the air valve during inlet pressure changes, making the terminal unit pressure independent. Terminal unit fan runs when the unit is in occupied mode, providing constant flow, variable temperature to the space. Here's the third kind of box. It's a parallel box, another fan box, and we use this one for perimeter heat or for heating in general because it can actually produce a lot of heat. We don't normally have if you use a regular box, which just has a VAV valve and it has a little strip heater here. With this one, we can have a whole bunch more heating air to do a lot of heating. So what happens here, it's a parallel volume box. It has a fan, but instead of being coupled to the outlet like the series box was, it's coupled to this plenum inlet. So what happens is the supply fan is on only when in the occupied heating mode. So it's not like a series box, it doesn't run all the time. It only runs in heating. When you're in cooling mode, this is a regular VAV box. So this cooling valve raises or lowers the air and it goes right to the space. During the heating mode, it sucks the air from the plenum and blows it and blends it with the VAV air to the space. So it's different. It's still running. It's on all the time. It doesn't go on and off. It's not variable volume. It's constant volume. It's like this. So it basically, velocitrol again is providing pressure independent operation. Uses interior heat of the plenum. We get to use the heat from the plenum. Fan induces plenum return air in heating mode. Supply air is constant volume in heating mode and variable volume in cooling mode. So it's one kind of box in cooling, one kind of box in heating. Hot water electric reheat coil if desired. Sound attenuator desired. Its sequence is identical basically. Room temperature sensor modulates the VAV damper and electric heater or hot water coil valve to maintain room temperature. Supply inlet velocity sensor maintains constant flow of the air valve during inlet pressure changes, making the terminal unit pressure independent. Terminal unit fan only runs in heating mode, providing variable flow constant temperature during cooling mode and constant flow variable temperature in heating mode to the space. It's like, again, I tell you, we're using these a lot of times in perimeter heating where this is a pretty big heater and a fairly good sized fan. So it's able to heat more than it is to cool, if that's what you want in the space. So those are the three kind of boxes: a regular box, series box, and a parallel box. So here's another system. It's called a VVT system, which actually stands for very variable temperature. And it's based on using a standard package AC unit that's not a VAV unit. This was developed back in the 70s when we had VAV air handling units, but we didn't have VAV package units. So to do that, I didn't, but someone came up with this system. And basically what it is a standard package system, air conditioning system, with a supply duct system that puts VAV boxes in each space. Now, these are capable of using a full VAV box, just like the other systems, or else you can use these, which I call them cheap boxes. They're a little round piece of duct with an elliptical damper in them, and they're really inexpensive. They're just a round piece of duct with a damper and an actuator, a controller for the box on them. Much less than a standard VAV box, but it doesn't have a lot of sound attenuation because it's just a piece of duct, right? So it's no big deal. I built an office building for my last company, from my mechanical company when I had it, and I'm a cheap guy, so I built these into it, and they worked really, really well. Well, when these first came out, they didn't work so well. So here's how the one we use today, if we use one, should always be this way. You have standard package units, which the air comes in from the return, blows across the unit, comes out, it goes to the VAV boxes, and these are closing off air when you need it. Well, this is a package unit. It can't have variable volume air. So what we do is we put a velocitrol right here, and we open and close. We modulate this damper to maintain constant flow across this coil. So the air is always, it's either running this way or it's running bypass. So this velocitrol always sees constant velocity, so the volume of this unit doesn't change. What it does is if we're using air and we got enough air, we don't need anybody to start shutting down, more air is going through here, so now all of a sudden this unit sees, whoa, it got cold fast, it can shut off the compressor. So it's basically capable of doing that. There's only one little issue with this system, that this system is capable of heating and cooling, because it's a package unit, right? You can put strip heaters down here, but normally we don't do that. Normally these are cooling only valves. So what happens is when it gets the space, we have these space sensors out here. They're communicating with the controller on this unit. It says, it's getting cold. We need some heat. Our dampers are down at minimum flow, so we need some heat. Well, this unit switches to heat. Well, the problem is these boxes now have to become heating boxes. They were cooling boxes. Now they're heating boxes, which means their polarity must change. So when you're a cooling box, and it starts to get hot in the space, you need more air. So you open the damper to get more air. When in winter mode, when it's cold, you're in a space, and it's cold, you need more air to heat. Well, that's the opposite of cooling mode, right? If you had cooling boxes in heating mode, they'd try to shut down, right? It's already hot enough. We need more cooling, right? So they would be making it backwards. So what we do is the controller that's running this unit sends a signal down to these controllers saying, you are now heating boxes, reverse your polarity. Goes back to cooling, you are now cooling boxes, reverse your polarity. So originally when these came out, these didn't work very well. And the reason was there's several units. I've retrofitted many of these systems. Originally they didn't think about this damper like this. They just come up here and put a damper right here in the duct and blew down into the return air plenum. And said, we can make it VAV, we don't need this connection. Well, what happened was, since they weren't tab people, they didn't figure this out, is that when you open air like that above a plenum, you think, well, it's wide open. Well, it has microclimates above there, and it will pressure that zone right where it comes out. And if you have a return damper in there, a return grill, it'll dump that cold air supply duct right down on the floor because it wants to go down, right? So the cold air will hug the bottom of the ceiling, and it will drop right out of those ceiling grills. So eventually we got the idea to put this hard duct this up, and that actually worked. So when they were just open them, didn't work at all. The other problem was we didn't have good DDC controls. We were trying to do it with electronic controls, which are not DDC, totally different. So we had to do a whole bunch of Mickey Mouse stuff out here. We had to have zone controls, worrying about cooling and heating and being able to switch over, and it was very complicated to do electronic controls on this. and it made it so a lot of systems just didn't work well. People couldn't deal with them, so they basically ended up ripping them out. But nowadays they do work, and they can work. But remember, the application is they're either cooling or they're heating. You can't have this unless you have strip heaters. You can't. This one can't be cooling. This one be heating. They're all in cooling or they're all in heating. That's the limitation of them. We have a DDC overlay. Remember, this is a standard package unit, so it has its control connections up here. This controller now is running this valve. It has this velocitrol, and it has a temperature sensor because the space temperatures no longer run this package unit. So that's how these work with the systems. Other than that, it's a standard package unit. I think in my office I had two 15-ton units I ran this way. And actually, it's my office and the rest of the office that work really well. But they have to be designed correctly. You can't have a real oversized unit, and you can't have too small a unit. This unit has to be the right size for this to work well. But I found it to work. Use standard AC, uses VAV boxes, uses small office occupancy with few zones. So if you have a building that has a lot of package units, and there's one area that's got 4 or 5 offices, and they all have equal importance. I always laughed when I was a control contractor. They asked me, "Where do you want the thermostat? Where's the boss?" That's where the thermostat goes. Well, in these systems, you can put 3 or 4 zones, 5, 6 zones off of a package unit without a problem. You can do that. VVT AC unit issues, called a poor man's VAV, doesn't quite work as well as a real VAV. Performance is not as efficient as a real VAV because we're doing a little cooling and heating in the space because we can't heat and cool. We can only do one or the other. Energy performance is less than a VAV. The sequence is simple. The supply fan should run. The outside air damper open anytime the unit is in the occupied mode. Modulate the unit bypass damper to maintain a constant velocity at the velocity set point. Stage the compressor and strip heater to maintain supply air duct temperature set point. It's a really simple sequence. It does work. Reset the supply air temperature set point every 5 minutes. Monitor all VAV box positions. In cooling mode, if any damper is full open and no damper is in the minimum position, decrease the supply air set point 1 degree. No damper is full open and 1 or more is at the minimum position, increase the set point 1 degree. Reset range should be 55 to 70. In a heating mode, if any damper is full open and no damper is at the minimum position, increase the supply air set point 1 degree. If no damper is full open and 1 or more dampers are at minimum position, decrease the supply air 1 degree. Reset range will be 75 to 95. Monitor the room temperature, room humidity, supply duct temperature, and supply air, and fan status. There's no return fan. That shouldn't be in there. But anyway, that's how this works. The thing about this reset is important. That's probably another reason the original ones didn't work. We didn't have any reset. But the reason that you want reset is because you can't heat and cool at the same time. You want to be able to make sure your temperature requirement is within the band of your airflow of the box. And to do that, you want to reset them so that you don't have any real cold boxes. And this reset's pretty simple. We don't have pressure to contend with, so we're just doing temperature. And we can't do that. And this is a VVT package system. Now there's VRF systems, which stands for variable refrigerant flow. These are quite popular nowadays. Unfortunately, just like everything else in life, your industry has fads and goes through fads, and some things become popular, then they fall out. Right now, this is popular. And it's popular because they're economical to install, and they're highly efficient in cooling. They started as a residential system in Japan. They're proprietary systems. They have proprietary mechanical systems. They have proprietary control systems. That is what is going to be their Achilles heel. Because what happens here, I'll explain these systems. We have a bunch of different evaporators. You can have ductless units. You can have ceiling cassettes. You can have regular fan coils out in each space. And then you have a large condenser. You can have a condensing system. So we're running many evaporators off one condensing system, and they have what they call control valves. And these boxes basically what happens in the condensing unit, it has connected to every box, every zone box. It has a suction line, a hot gas line, and a liquid line. So this box can divert these to different controllers. So if this needs to be in heating, this box will divert hot gas and the hot gas and the suction line will go to there. And if this one needs heating, it'll put hot gas. But this needs cooling, it'll put the liquid line and the suction line. Liquid line and suction line. So it's capable to make, this could be in heating, this could be in cooling. That's what's different than that VVT system I showed you, which you can't do that. This can. This have VFD compressors on the compressors. It has VFD supply fans. On the evaporators, it has VFD fans on the condenser fans. It has poor heating performance, unfortunately. Like a mini split, this has a very high cooling efficiency ratio. You can get them up to 24 SEER in cooling, but in heating, they're just a heat pump. So they have problems when it starts getting below 32 degrees Fahrenheit. They'll go down to maybe 20 degrees, but their efficiency is really poor at that level. So what we normally have to do, if these are put in cold climates, we have to put auxiliary heat into make-up air systems, and normally it's gas heating because it needs to be a lot of heat because these don't heat. These can have oversized crankcase heaters on them, which will put a little heat to allow them to operate a little colder, but they're not operating efficiently at those cold temperatures. You use gas like in makeup air. Very energy efficient in cooling proprietary control systems. I did a large one for the government, and the engineer told me, he had a little black box on the drawing, and I said, well, how am I supposed to control this system? And he said, well, the salesman for the VRF systems guaranteed me this system will integrate seamlessly to your control system. I said, okay, so I got to figure this out. So I went and figured it out, and what happens is they allow a backnet integrator into the system that allows us to get onto it and to be able to see it. So I said, okay, good, not a problem. So we built it, and when I got there, I learned that the points inside of VRF doesn't look like any points inside of our systems. So the word seamless integration, not so much. It turned out all we could actually do is we could stop the system, we could enable it, disable it, we could reset the temperature set points in the space. That's it. You know, we could see a few things. We could see a few alarms, whatever, but that's all the points it had. And that upset the engineer a little bit, but nothing I could do about that because he took the word of a salesman, which sometimes is a problem. So anyway, that didn't do that. Now, the Achilles heel I mentioned of these is the proprietary systems. So remember, this is mechanical systems, all proprietary. There's about 5 major manufacturers of this around the world. Carrier is one, Mitsubishi is one, Hitachi's another. They have a lot of different manufacturers, and every one of them do these things differently. These valve boxes cannot be used from one manufacturer to another. I was serving on the PDC of ASHRAE, which is the Professional Development Council Committee, and we were actually developing training resources for the engineers at ASHRAE, and we wanted to develop a VRF training course so that the engineers could learn how to design these. And we ran into a problem because each manufacturer had different components and they all pipe differently, so they don't even pipe the same. You know, one manufacturer you might be able to do 2 fan coils or 10 fan coils. The other manufacturer maybe can only do 8 fan coils. So if you had one system with 10 fan coils and this thing broke, well, you got to buy the exact part, model number from the exact manufacturer for that to work. If for some reason that manufacturer no longer makes that product or that manufacturer's gone, you're hosed because you can't just buy another brand, put it in here. You end up having to change every piece of equipment in the system. And if they pipe differently, guess what? You got to rip all the piping out and start over. Well, people are not going to notice that until these get near their end of life, and then they're going to notice it big time. I mean, the proprietary controls is a little irritating, but proprietary mechanical is a killer. You know, it'd be like you putting in a fan coil unit on a chill water system that's proprietary, and you'd have to tear off all the systems out to put a new fan coil in it. That's crazy. Well, these are that way. So the This is going to hurt this manufacturers one of these days, when it's time. Sequence control here is pretty easy. Since the VRF system is totally proprietary, there's no programming required. The install selects from pre-programmed menu items to include. Integrate the other control system is possible by using a BACnet integrator to translate point data from the VRF to the supervising control system. The issue is these were created from residential systems, so the points are different than a normal control system. Point list is very restricted to normal items such as room conditions. So it's hard to explain, but the room set points were all about a residential environment condition, and instead of just changing temperature, you went to a different environmental conditions, which didn't work in our commercial world very well. Mini splits are basically our VRF system. These are just one zone, but they have a variable speed compressor, variable speed fan, exactly like the one we just talked about. Small rooms, VFD compressors, very efficient in cooling. They don't have any control sequence. They're self-contained. The only thing that's interesting about these is they come with a little remote, looks like your TV remote, and that's what sets the temperature and sets the schedule for this. For a commercial system, you really shouldn't have that, because if someone loses that, you don't have any control over this unit. So we always specified these to have a wall-mounted thermostat, and these is available as an option. You can purchase a wall-mounted thermostat that wires up, and it's not just laying loose somewhere. So that is what you need for a commercial. You don't need that thermostat, that remote walking away. And that's it for commercial package systems. Package units are interesting systems, and I hope you got some good out of this. I really appreciate you being a subscriber. Appreciate you watching the video. Please share with your friends and neighbors. I'll catch you on the next one. Thanks.